Yeah, so I was asked to come talk about literacy in scientific computing, and it's something that somehow I've been roped into doing since I started participating in software carpentry. And it's a little weird to talk about literacy in scientific computing to a group that's congregated because of their love of a particular file format. But I think it's a concern for all of us. You're all here because you are into scientific computing, and you are here to specifically learn about Python. But our colleagues, most of our colleagues, are not, which is terrifying. Because most of the data we're seeing in papers, it's coming from somewhere. Probably Excel, probably done by hand. Atmospheric scientists are better than the rest of the geoscientists, but that's scary, because we don't know what's happening in the background, and we are believing the numbers. And you know, if we just improve scientific computing in the community, then we are definitely going to improve our science. So, you know, we started the workshop looking at pictures of the first workshop with giant white boxes on desks, and now we're all using tiny little computers that are super powerful. And you know, that was the 80s, and the reality is that things are accelerating, and it's the technology and the availability of this technology is increasing really, really rapidly. I think Google Earth is a very good example of this. When I started as an undergrad, my first job was compiling satellite imagery for a grad student, and it was awful. Everything was covered in clouds, and it was super expensive. That was not that long ago. And now, Google Earth, you go and you find whatever you want really quickly. But you know, the first Google Earth really just came out in like 2007. And we feel like it's always existed. And having this technology available, both for scientists and the public, is actually changing the way people think. I really wonder if people's spatial abilities are changing just because now we look at aerial photography and imagery all the time. And you know, one of the founders of Coursera, which is one of those online teaching sites, has said it. It's the things that we're using now, the technology we need to know now, didn't exist 5 years ago. So even if we teach it to students, it's already going to be obsolete by the time they graduate. So this is the concern. We have to teach it to ourselves. Again, talking about imagery, it was very obvious with the Nepal earthquake. Immediately afterwards, we had imagery of what had happened. This came from the Washington Post. These are digital globe imagery. On the left is a before picture. On the right is an after picture. That picture is from 48 hours after the earthquake. They had imagery 24 hours after the earthquake. They immediately sent the order to the satellites to start taking pictures of that particular area because people expect it, people need it. This is being used for, you know, rescue operations and so on. And we have the technology, so we use it. And they are leveraging that technology for the greater good, let's call it that. Digital Globe has a platform where they crowdsource the categorization of imagery. So I did this after the Colorado floods. They open the site, and they just give you an image, and they tell you to put dots on things that you see. So destroyed house, and flooded field, or something. And they did it in Nepal, and that's what the map looked like about a week after. And every single dot is something that someone had categorized. And the scary thing is that they gamified the process. So if you clicked on something, it would tell you 87% of people agree with you. And it was really addicting. And they gave you points, which meant that you actually spent hours and hours and hours doing this. And then they fed the data back to the on-the-ground rescuers, at least here in Colorado. So then they knew behind this house that you can see from the road, there's a shed, and the shed is destroyed. You should go check out the shed that you wouldn't know about otherwise. And it apparently really helped. So, you know, this is a technology we're all using. And I am a geologist. I pretend like I work with rocks, which is really not true. But in the geosciences in general, we are the ones that still would use mules if we could. Atmospheric sciences and the planetary sciences have had to modernize because their data comes from, you know, remote sensing and things like that. But geologists are still very traditional. So this is G.K. Gilbert. He's the father of modern geomorphology. You know, white male, beard, fairly common as a geologist. And you know, anything we want to do, he has done before. He has done it better, and he actually did it on a mule. One of his greatest papers has that map. It's a first description of the Henry Mountains, which is this mountain range in southern Utah, last mountain range to be named in the continental US. Beautiful place, just north of the Bullfrog Marina. If you've ever been there, it's quite a peculiar place. But there's this map, and the map is a shaded relief map of the Henry Mountains, and this was published in the 1877. The thing is, that image, it really is a shaded relief map. We think that geologists are low-tech, but even back then, he was using the technology of the time. That map was built as a physical map. Someone carved it from data they had collected on the ground, and then took a picture, they took a photograph with the lighting just right. And it's a shaded relief map. So I went into Google, and I just did a screenshot of the same area with modern, you know, SRTM data or something. It looks exactly the same. That's a shaded relief map we made digitally. That's a shaded relief map they did in clay, or I think actually might have been wood. But you know, geologists do use technology. We just tend to forget this. But the problem is that we just don't know what we're doing. No one teaches us how to do these things. But at this point, software is kind of the lab equipment. Not just because there's no funding and computers are cheaper than fieldwork, but it's what we do, it's what we need. Obtaining data, you guys, now involves a lot of coding. My first venture into trying to get the NetCDF libraries installed on my computer was so much fun. You know, I knew what I was doing. I wasn't scared of the terminal, and it was a disaster. It's not really that much easier at this point, you know? Most people don't know how to use GCC. And you know, at this point, our data is just too big to analyze by hand. You know, we have millions and millions of points if we use LiDAR for topography, or you know, our sensors collect data for 6 months, and we have so much resolution. It's ridiculous. Excel will crash if we try to do it in Excel. Definitely cannot do it by hand. So we need to learn how to program. And a lot of what we do really is writing numerical models. And writing mathematical models requires programming. We can't solve nonlinear equations by hand. I mean, we could try, but it's hard. So we program. And that's what it's expected right now. If we want to make testable predictions, we need to be able to program. And again, we're not teaching this to students, and that's a problem. So I went to MIT, so I'm very nerdy for the community, so I can pick on them. I went to the website and got the undergrad curriculum. This is a department that produces planetary scientists, atmospheric scientists, and geologists. None of the required classes involves any programming. Of the classes that, you know, huge list, you can take 3 of these. The ones on the bottom left have some programming, mostly MATLAB. And you could take a couple of intro to computer science classes as one of your optional credits, but that's it. So Sean's grad student from yesterday who came in and was doing Python, he's imaginary. Most likely, if you get a grad student, they will not know how to program. And you know, this grad student's advisor was really nice and just handed him a lot of data, but it's going to take them a while to get going. And therefore, we should be concerned that the people coming into our community have no training in the things that we require them to do. So I was going to show you the University of Colorado geology curriculum, and it was so sad, I just decided not to. So even the nerdiest schools are not teaching computer science to geologists or geoscientists. And because we don't know what we're doing, we're just making it up as we go, we're really just wasting our time. I mean, spend so much time just fighting computers and fighting for the thing to compile and fighting for the thing to I don't know, just behave, have no idea what it's saying, spend all day Googling, hoping that someone wrote this in some Stack Overflow question and that the answer makes some sense. But we do it, and we consider it a bit of a tax. We have to program because we have to program. We don't want to do it, we don't like doing it, we don't know how to do it, but we have to. And yeah, we're just wasting a lot of time. About 90% of researchers, and by this I mean scientists and engineers, are self-taught. I have never taken a formal programming class, and I'm theoretically a developer and something. I don't know about most of you, but yeah, most people have never actually taken a programming class and they're doing science. So we don't know what good programming looks like, even if we teach it to ourselves. We're kind of making it up as we go. And we don't know what we don't know. We don't know if there's a better tool. We don't know if the tool we're using is not really meant to do the thing we're using it for, and so on and so forth. Therefore, even if you know how to program and your grad students know how to program, you should be very concerned about the fact that the rest of us just don't know. Computers are wasting our time, but they don't really have to. Good programmers are about 10 times more effective, more productive than the average programmer. And it really doesn't take that much to go from totally mediocre to slightly okay. And there's a big jump in productivity just between those two. And what that involves is automating workflows, so not doing things by hand, so they're repeatable, so you stop making mistakes, because once you type the same thing 100 times, you start making mistakes. Science should be repeatable. There should be a record of what we did. Automating our workflows makes us more productive just because of that. And it's also starting to think about code testing and code validating. And scientists in general, if you survey them, they'll say, yeah, maybe I learned some software design. No one ever taught anyone about testing or about validating code, and no one does it, because it's what happens after you get your results for most people. And at that point, you have a paper to write, and you have something else to do, and you just don't do it. But if we did, we would find bugs, and we would fix our code, and we would be better scientists. So I wanted to give an example of all the ways you can improve as a scientist. I'm using a netcdf file, and I just want to make a movie of some model output. One of my models produces netcdf files. And then I realized that I couldn't actually tell you what I would do by hand or automated, because I have some crappy old MATLAB code that turns it into some slightly more readable ASCII file that I then can put into something, and I wrote it years ago, and I'm not touching it, and it's even faster to just run that MATLAB code than for me to rewrite it in Python in some elegant way. So I just keep using it, and I know it's wrong, and I know there's a better way, but I just don't do it. And that's a problem in science. We all do this. So I'm not going to talk to you about how to do with netcdf files, because I don't know. ArcGIS is something I use all the time. It has just taken up years of my life. It's a software that you use if you're making maps, if you're dealing with topographic data. And there's a lot of data. It's heavy. It's slow. ArcGIS costs thousands and thousands of dollars. It's ridiculous. They can do whatever they want because they're the only one in town. So if I just want to get a bunch of rasters and I want to stitch them together to make a bigger map, it's not very difficult. I can do it by hand, sit there, wait, because it takes time. It's fine if there's 2 or 3, but if there's 100, it's just going to take all day. Probably going to make a mistake, it's going to crash, because it always crashes. So I shouldn't do it by hand. They have a nice little GUI for automating the workflow. You can drag a bunch of little blocks, connect them together, and hey, it kind of works. It tends to crash, but it works. And I can let it go and then go home and then come back the next day and see what it did. Or I can write some Python. I went online and just copied that. That's about 1/3 of the steps it has to do. I just have to write a loop around that. That would do it all for me. It would be way faster than the GUI. And I actually don't have to write any code because it's all online. This is really automating the code. The GUI is a nice little middle step. Doing it by hand will be a nightmare. So what do you learn? We've agreed we need to teach people scientific programming, but what do we teach them? So I started making a list of all the things that people have told me I should learn, and this is all the things that I have at some point in my life tried to learn. This doesn't include all the things people have told me I should learn.
No Julia.
No Julia. That's true, actually. Of those, maybe I can read the first column. I won't say I'm fluent in any of them. I can Google really well for the first 4 or 5. Maybe use Python frequently, not fluent. But basically, I've just failed at learning scientific programming. Again and again and again and again and again. The only difference with the average scientist is that I succeeded, mostly because I had to. I had no option. My code was in Python. I had to use it. So what do we teach people? What do we learn? I don't know. Whatever works. Part of the problem is that it kind of depends on where you work and who you work for or with. Many of the things that you're supposed to learn, it's because someone's code, there's this little script in the archive that's in the backup of the computer that's now a footstool somewhere under the desk. It'll totally solve your problem. If you can just get that code to run, it'll just fix your problems. But, well, you know, it's written in Fortran 77. There's no documentation. There's no comments. But, hey, just get it to work. So maybe you'll learn Fortran. Or, you know, that computer that's actually held together by duct tape. I used to work in a lab. The computer, you couldn't touch it because it would break. But no one could rewrite the code that was running the entire lab. And it was some old PC that was all taped together. You learn whatever you have to make that thing work. So you're not necessarily learning the most useful or modern language. Just do what your advisor did. So if I look at my own line, I graduated last year. My advisor, he's fairly young. He got his PhD in 96. He's a modeler. He mostly works in C or worked in C. We've gotten him working in Python. He started writing Fortran because his advisor graduated in 77, my grandfather, wrote in Fortran. His advisor, my great-grandfather, was, well, he was a sedimentologist. And he was brilliant, but he did everything by hand. So I really shouldn't really learn what my advisor used because it's deprecated fairly quickly. So, and the problem is even worse. In my graduate career, Python has gone from being essentially non-existent to a fairly common language for scientific computing. It's happening so quickly that even if we teach undergrads, it doesn't work by the time they're grad students. So we're having to teach this to ourselves, mostly out of necessity, mostly because things are happening so quickly that we don't have an option. Perl is diving. People have been picking up Perl all week. I learned Perl because my dad learned Perl when I was a teenager. It's awful. So software carpentry has kind of said, just learn whatever makes it work. Just program decently well. Just good practices. Reality is more complicated than that, and what the best language to learn is kind of a cult thing. Computer scientists will say that you have to learn something that's really formal, like you have to learn C as the first language, but reality, you scare people away because it's completely incomprehensible if you know nothing. Python is becoming a really popular language because it's fairly easy and high level, but there's many of them. Doesn't matter, just learn the basics. All right, so I'm here because I'm part of Software Carpentry. Software Carpentry is an organization started as part of the Mozilla Foundation that aims to teach basic scientific computing skills to researchers over short workshops, mostly with the goal of getting them coding something. Good practices, they don't have to know very much, just need to know enough to Google. It started as a fairly small group. You know, they had big philosophical ideas of how this should be done. At this point, there's hundreds of instructors. They've run something like 400 workshops. It's a really major operation. It's all volunteers. There's some funding for the people who are managing the whole thing, but that's about it. We all do it as volunteers. And Software Carpentry teaches as a core either Python or R, mostly Python really, how to use a shell, because especially as we go into HPC environments, we're going to have to use the shell more and more, and you should at least be able to navigate. And version control. Big problem in scientific computing is that we have no record of what we've done. And that's on one side a problem because our computer crashes and we lose a lot of our work. But also, there's just no record of what we've done. We can't share our code. We can't collaborate because we don't know what we're doing. So trying to teach people how to use Git. Sometimes there's also some SQL, things like MATLAB, but that's the core of why they teach. And yeah, they're just teaching the skills that you need to be productive as part of a small research team. We're not talking about massive codes with millions of lines and a giant group. Just you and your colleagues, you can share things, and it looks okay. So they run workshops. They're usually 2 or 3 days. This is the latest count of the workshops that have happened. There's a 73 over the Northeast. It's about 4 years they've run something like 400 workshops. Each of them has something between 20 and 50 people, and it was true. Like, they do fill up within hours. I was saying we ran 2 at CU back to back. Same community we sent the messages to. One was Monday and Tuesday, then Wednesday, Thursday, Friday. Both of them filled up within 3 hours of sending that announcement email. We had over 100 people that just signed up. And it's not at that big university. There were not big departments that we sent it to. It filled up because people are kind of desperate. Everyone recognizes we have this problem. Grad students recognize they need to learn these things, and there's no classes. So software carpentry is filling that hole. At Boulder, around Boulder, we've done about 7 so far. There's 2 more going on this summer. And these are the ones that are currently in the upcoming list. And it's not all-inclusive. The 2 in Boulder this summer are not there. The ones in blue are the ones happening in June. So there's 5 or 6 workshops a day at this point. In January, we ran 30 in 30 days. And they're all filling up really quickly because people are desperate. This is what our workshops don't actually look like. We wish they looked like this. I just really wanted to include this picture. In my post-PhD funk, I started volunteering with this group that teaches coding workshops to little kids. And by little kids, I mean 6-year-olds. And this is what it looks like. In this particular one, they were making games using Scratch, which is this graphical programming language. It's really fun. Make these little cartoons move. And they were controlling them with Digital Sandbox, which is an Arduino that has pre-built sensors. So they could make noises at it or shade it, and the cat would do things. Little girl in pink in the corner, she's a superstar. She's 6. She taught me how to make functions in Scratch. And the little kid in green at the top, he's, I think, about 9. If you ever played the game Flappy Bird, he made Flappy Bird in 2 hours. The graphics were not quite the same, but it was freaking Flappy Bird. It was the game. It was ridiculous. We ran an iOS workshop. They made apps for phones. The biggest issue we had is that they couldn't spell. So variable names were difficult to keep track of. But it kind of gives you hope for the future. The thing about these kids is that no one has ever told them that they shouldn't be programming, that this is difficult, that this is hard, that they don't know enough. It's really shocking. Like, computers are just an extension of them. They go from playing Minecraft to writing mods for Minecraft, and they don't feel there's a difference. We wish we were like that. Getting to the point where you're a programmer that is confident enough to just think of a problem. It's like, oh, I can solve that. I don't know how. I don't know how to write that language. I don't know how to write that code, but I'm sure I can figure it out. That's what we want to do. We don't want to be limited by our tools, but we currently are. Software carpentry recognizes this problem. What's keeping a lot of people from learning how to program on their own is simply fear. Software carpentry instructors go through training. You go through a semester-long online class. Meet every week for a few hours. You do homeworks. You do screencasts. You do all kinds of things. And I was really shocked at how much of it was just psychology. Just talked about how people get demotivated, how people stop programming, how people leave science and leave computer science specifically. And a lot of it has to do with culture. Someone at some point told them they couldn't do it. Someone at some point gave them a code and then, berated them because they couldn't figure it out. And it was this thing written in Fortran, 20 years ago with no comments. So they just stop doing it, and they think they can't. So in workshops, that's what they actually look like. Not nearly as fun. Still a lot of fun. A lot of what we do is just getting them to a point where they have a working Python installation. We use Anaconda. They're using the IPython notebooks. They have a working Python installation. They've written some code, and it worked. It wasn't particularly complex, but it worked. And now they know how to open it, and now they know how to write something in it and make it work. And just that builds enough confidence that then they can go learn it on their own. In thinking about this, I started thinking about how I learned to program. I was really nerdy. Got, for Christmas, when I was about 12, a book on C, programming in C. And I never literally learned C because, well, A, the book was in Spanish. Okay, Spanish is my first language, but it's like trying to navigate a computer in Spanish, it doesn't mean the same. Like, the words just don't quite mean the same. So it was really hard. And two, I never got a compiler to work, to reliably work. And the books just assumed that I knew what a variable was, and I didn't really know what a variable was. And it's those things that we completely take for granted. We know what variables are. We know how they function. We know how they change value. That if you just go through the computer science track as a non-computer scientist, they just kind of never teach you. But we have to be concerned about those facts as non-computer scientists. So the software carpentry workshops usually are based on 2 or 3 basic concepts. One is peer instruction is much more effective. So you sit at the same level as people, and usually the instructors are scientists. They're not computer scientists. They don't know how to program either. They taught themselves. And it's really helpful, actually, when you don't know the terminology. You're keeping it very simple because that's how you understand the system. And the other one is that we do live coding. We have an open IPython notebook, and we're coding live on the screen. People who are really good programmers will actually connect a second keyboard that's slightly different from their own, so they intentionally make mistakes. So they mistype things, so their code doesn't run. Making mistakes on the screen, it's incredibly difficult to learn how to program like this. But people seeing you make mistakes means that if their code doesn't run, it's fine. It's probably just a typo. I mean, it's exactly the same thing you just did. And there's a big difference between having someone talk to you from the front of a class telling you how things are and just kind of following along with someone who's kind of struggling with you. And it builds confidence, and it means that people end up coding. And we do fun things. So this was a Women in Science and Engineering workshop at CEU. It ended up being this giant love fest. I mean, they still get together every week. Like it was amazing. There's a comment at the end that was tweeting from the workshop. That's cheating. That's amazing. Wow. We're showing the matplotlib. Turns out matplotlib has a built-in library to make things look like XKCD. The trend of global warming, XKCD style, hilarious. Not nearly as scary. Talking about Git, the top, we'll learn about conflicts and how to resolve them only in a text file sort of way. It was funny. So the lessons in software carpentry look something like this. They are IPython notebooks. There's some markdown text, and there's little things you can run. And this is the level of them. It's really simple. Make variables, make functions, import some files, plot some things. We just want it to work. It's not like you can learn that much in 2 days anyway. Just know enough to go Google. So for example, it might look like this. There's some text, and here's a little piece of code. then you go on a screen and you're live typing, and this is what it looks like. So the teaching in software carpentry, and I think the teaching that as a community we should be trying to instill in people, is that we just need to use good programming practices. And there's some very simple ones that actually kind of go against what computer scientists might tell you. It mostly revolves about making things work and worrying about how elegant it is later. You should be writing programs for people, not computers. Small, self-contained little functions that you can exchange in and out. You know what they do because it's really simple. And if one of them breaks, you know where it is, and you can fix that one function. It's kind of difficult to, when you start programming, to think like that. Then you just let the computers do the work. We're lazy, you know? If the computer can do this horrible, horrible thing for you, just let it do the horrible thing for you. Stop trying to do the work by hand. Of course, at the beginning, it's easier to just do it by hand, so we keep doing it. And it's hard to change that mentality. Another good programming practice that we all tend to ignore is to make incremental changes. And this goes back to teaching people how to use version control. Don't just work all day and then, oh, it broke sometime this afternoon. Don't know where. Change a little thing, and then check it. Change something else, check it. And have versions and keep track. Because otherwise, then you'll spend years debugging. Don't repeat yourself. Again, write functions, reuse them. Don't reinvent the wheel. I love reinvent the wheel. I'm sure it teaches me something, I am sure. But I can just import a library and then levitate, you know, with anti-gravity. Testing, write assertions. You're going to make mistakes importing your files because you're going to be sleep deprived when you're finishing your PhD, or something. But also, in 2 years, you might come back to your code and you don't remember what it is that you were supposed to import here, what the variable was supposed to be. So just check. Make sure your code checks that the file you imported is the thing you're supposed to be importing, for example. Just make it work. Just make it work. It's not pretty, it works. Then deal with it. Then make it go faster. Just make it work. Have a tendency to try to make it work elegantly, now that I know just enough to be dangerous. Waste a lot of time trying to make it be elegant, but something that we should keep in mind. You should not be documenting mechanics, but you should be documenting design. You know, you can read the code and figure out the thing is a loop. What were you intending to do with that loop? There's a really funny Reddit on best comments you've ever seen in code. Should have brought it up. There were a lot of, I have no idea why this does it, but if you set this variable to 1, it'll explode, so just leave it at that, or something. That we shouldn't be doing. But I guess that's documented design. Some felt it was necessary to comment about the fact that you shouldn't change the variable. And then collaborate. Something atmospheric scientists and planetary scientists, again, are modern. Geologists are awful at this. We just don't share our stuff. We just don't share our code. And we definitely do not work together on code. I am now part of CSDMS. Some of you know people from that group. We are using supercomputing to do landscape evolution modeling, coupling models, and things like that. Have giant models, and people just don't collaborate because no one ever has to. You just write your own thing, and then you use it, and you hope it works. But if we collaborate, then someone's checking your work. If you made a mistake, someone's going to see it. Your code will survive you, or has the ability to survive you. You know, there's this fear that your thoughts are, well, for one, they live on your computer, that can crash and take it all with it. But all this amazing work has been done, and then it disappears because someone retires or something, the computer crashes. And because we collaborate, if we collaborate, we can build bigger software and better software. And it's getting to the point that as geologists, we need it. You know, we can no longer get away with little MATLAB scripts. We have to build bigger things. So the conclusion from all of this, and again, you guys are here because you all share a file type. But as a community, we need to be instilling better programming practices on everyone, on scientists, because by having better programming practices, we end up being more productive as scientists, and we end up doing better science because, well, it's reproducible, we know what we're doing it correctly, and also, it's a tool. It's like the little kids. I want to be able to just feel like that I can do whatever I want because I can code it. Of course I can code it. I mean, I don't know how to do it, but I can do it. And we have to get to the point where we can all do that instead of being completely limited by our tools and the tools that we have. Another tweet from that workshop. It was really all lovey by the end. So use of the stickies, and now you guys start to do it, and I still have not seen the perfect use of stickies. But there's something empowering about being able to, put a little notice of the way things are working at the workshop. And someone was really, really happy and had a little drawing of a happy sun. Cool. So I was debating what to do. I have 20 minutes left. Since, well, for one, I'm sure most of you have taught more programming than I ever have. Most of you probably are more fluent than I am. So I thought I would just do a bit of a mock-up of Software Carpentry Workshop. Partially so because I think there's some good practices that I hope people can adopt, but also because I want to get ideas of how to do it and how to do it better. Something we're trying to do is to have little spin-offs and start customizing the lessons. For example, there's something called Data Carpentry now, which is like a little sister organization, which is focused more on data processing and how to handle data and how to write metadata. And for example, the Python, still teach Python at a novice level from absolute zero, but it's mostly using the Pandas library, which makes it handles things kind of like spreadsheets. It's amazing. Another one that we're trying to make is a GeoCarpentry. So more visualization, more big data. And I'm curious to know if you guys have any ideas of how to do that better. There's a big push from Geology and related departments to have more workshops. So if that's agreeable to people, so that's one option. The other idea I had was to put you all in an environment where you did not know the language and see what would happen. So if you prefer to do that, I can give you that option. So Scratch versus Python? Scratch? Yes? No? Okay, I'll show you Scratch if you want to work on that. Play with that while I'm... So scratch.mit.edu. It's a download that you can download some software too if you want to run plugins and things like that. But if you go to Create, it's a little editor. And don't look at the tutorials. Don't look at the help. You know nothing. Now go make the cat do something. So the whole idea is to make the little cartoons be animated and do things and respond to you. So you have little scripts, and you can, for example, say, where is it? When I press the space bar, you should stamp the image and then move it 10 steps. What can I do? Think, and then play the sound meow. That one. It's really fun. You can actually import data. There is an extension to visualize weather data in Scratch. You can do all kinds of things. It's really, really great. So if you want to play with that, I will just walk you through what a software carpentry workshop might normally do. So we assume people know nothing. In many cases, people do know programming. But we really assume that variables are a completely new concept to them. And we partially do that because no one will admit the fact that they're not completely comfortable with the fact that variables change value, or that they only have one. They actually only have one value to them, and you can change it. And what is a pointer and what is a value, and how you refer to them. So we just assume they just don't necessarily know this. We never talk about, at the novice level, we don't talk about classes. We don't go past functions. Classes are complicated. So as long as they can write functions, they can eventually learn about classes. We always have an Etherpad running in the background. An Etherpad is kind of like Google Docs, communal editing of a file. And you can write things. You can write something. People have lecture notes going and collaborate on them. And usually we have multiple instructors, and some instructor in the back has, it's kind of maintaining those notes. And the more advanced learners are contributing to those notes. And there's a little chat window. Oh, there's people. Hello. And you can type on the chat. And in small workshops, there's usually enough helpers and enough instructors that if anyone has a red flag up, you can go help them really quickly. But sometimes you have 50 or 60 people in a room. So they ask questions on the chat. And then if there's an instructor observing this, they can answer questions, or some of the other learners can do it too. And then we just walk through the lessons. So I'm going to do that. So the first thing we do is teach people some bash. Windows users, when they install Git, they get Git bash. And we go through that. As you all experience, well, some of you experience with Anaconda, that there are issues with the libraries. But that's usually the biggest problem we have with the software side of things. The other problem we have is that Mac users might not have the developer tools installed, which means they don't have compilers. And I think this is really illustrative of the state of a lot of people in the community. They just don't know that they don't have the compilers because they've never had to use them. And these are grad students at a good university in departments like physics. So it's a much more widespread problem than we think it is. So we start with an IPython notebook. And we're doing all of this live. And this is going to work, right? Come on. There we go. Yeah, so by this point, so I'm going to start in lesson 5 of maybe 7, then novice level workshop, when you're really talking about very basic intro to Python. So if, say you want to talk about functions, might say, functions are like tools. If you want to, say, print something, you'll say print hello. And it prints hello. And that print is a function. It's a little tool. And it comes in a big toolbox. So you might say import numpy as np. Numpy is a big toolbox. And inside it are little tools. So if I say np, that's just an alias, array, I am pulling out the tool array from the toolbox numpy, and I can use it. And at this point, I usually like to show this photo from the Mythbusters workshop. If you look at the background, Mythbusters, they have walls of boxes labeled things like rubber hoses and explosives. And that's kind of what libraries are in Python. They're giant boxes full of other stuff. And sometimes they have boxes inside. So you can, from matplotlib, import pyplot. And that's just a box inside a box. And that will have tools inside itself. And when you write a function, you're just making your own little tools. And you can import them to yourself. And you can share these if you're good enough. And you can reuse them. So I think that gives a sense that what you're doing is bigger than just writing a little function, and that these libraries you're importing are not mysterious and like overarching, and you can never reach that point, which is the truth. And again, it's about getting to that point of kind of empowering people to just code.
Can you show us what's in NP? Or do I have to go off on some other?
No, so
Google it somewhere.
Oh, you can Google it. But the notebooks are really nice in that it lets you interact with Python. So if I type np for numpy dot and press the tab, it will offer you everything that's available. Which is really helpful. So if I say np array and write the parentheses and then do tab, shift tab, it will give you the doc string. So you can open the help immediately. So functions have there's some parameters you can pass to it. And in this case, the parameters are an object. You're passing something to it. And you have some optional parameters like dtype and so on. So I'm not actually covering the material. I'm just going through the motions. So define a function with def. And that's just saying, this is a function. This is a function. And this one doesn't have any parameters. And this one might say hello. If I just run it, nothing happens. But the function is defined. So now the computer knows that if I say this is a function, it's like I said print. It's just added it to its list of names. So if I call this is a function, that didn't work. And this is something that's very valuable about typing live, and that is that, well, you make mistakes, mostly because you're not thinking about it. So it is a function, so I have to give it parentheses because I have to pass it nothing. And it says hello, because that's what I'm telling it to do. And whatever I do is just going to do the same thing. Same thing we can do is convert temperatures from one unit to another. So if I say temperature in Fahrenheit is 32, I can then maybe convert it to Kelvin. So I actually had to write this down because I don't use Fahrenheit. Again, you Americans and your imperial units. So if I say temp minus 32 times 5.9 plus 273.15, and it's going to be my temperature in Kelvin. Temp is not the final, yeah, there we go. Okay. Okay. Now let's say my temperature in Fahrenheit is boiling point to 12. I can copy this again. It's not a function. I can, come on. Temperature in K, there's something wrong with my code. That's not what the answer should be. And this is the first time, really early on, they've only been using functions once. Introduce the concept of testing and making sure you have tests in your code. If I just test my function with 32, my function works. I mean, okay, so we can turn this into a function, but let's turn it into a function. F to K, temperature. If I just test it with 32, I think it works. And that's what most people will do. But if then, oh, you used a different temperature, it's wrong. And then we start talking about integers and floats and so on in Python, and how to cast things as floats or integers. But we're doing it all by making mistakes live and mistyping things and not quite figuring out and wondering what is going on and asking another instructor in public because, well, that's what you do. And what I found is that it makes a big difference. If you just stop pretending like you know what you're doing, people are willing to experiment. And something that I've been trying to do, and this is, after more and more workshops, is really early on, give them an exercise that they have to do on their own. We had one at this WISE workshop where you started with an estimate of the production of sugar in the world and ended up calculating the number of people who like the color pink by going through some estimate of how many jelly beans were produced and what proportion of those were pink. And it actually worked. When we could plot it, it was really funny. And there's another one that I'm working on for a new workshop where start with a really dirty file and then use regular expressions really simply to turn it into some clean, nice document. It's something that you might spend hours doing in the text file by hand, but it's a bit of a superpower. And you don't need to know very much. And you can give people a file, and they can give you an answer. And it's incredibly rewarding, and you can only do it through trial and error. And after that point, people get aggressive in a workshop. They start asking questions that just, it's going so fast. They're so interested. They're testing everything. And it's empowering. And I hate using that word. But it actually does change the way people interact with computers and interact with code. And I think it's what we should be aiming for as scientists. So I really didn't know what to do about a hands-on workshop for you guys because, well, again, you've all probably taught more than I have. If any of you have been to a software carpentry workshop, every instructor has their own flavor, and we all kind of start creating our own materials. But there's a general overarching kind of path we're all trying to follow. And this push for a geo workshop is really, geo carpentry is something that we're all interested in. So if you have any specific ideas of anything you would like people to know in the community, anything you would like your incoming students to be able to learn really quickly, I would love to hear anything you might have to contribute. We're always looking for instructors, and I will recruit anyone who's interested because we're desperate. Like really desperate. I'm on my 5th workshop this year, and it takes up a lot of my time, and we really need more. So if you can be recruited, I will recruit you. So yeah, thank you. I really hope that things like this happen more often, and that we actually interact as communities. I was saying earlier, there's so many people in Boulder doing the same things I do. I don't know any of them because we just don't interact. So more things like that, bringing more students, I think would be great. Cool. Thank you. I am curious to see if anyone actually played with Scratch and got anything to work. Okay. It's fun.
Thanks very much, Mariela. Questions? We've got a few minutes. Mark?
I was kind of curious about the little workshop with the kids. To me, that's a fascinating aspect
amazing.
as well, too. One of the things we're trying to do at our research center is develop an environment where we can bring in outside students. And I hadn't thought about students actually at that age.
We've had 3-year-olds. It's insane.
So I was kind of wondering. With the little kids, do they, at that age, especially the 6 and 7-year-olds, do they tend to work individually, or do you promote kind of a community engagement with the other kids? So getting together, saying, "Hey, let's solve a problem together," or "What are your ideas?" I know after the products are kind of developed, it's like a show and tell almost.
So we do a lot of different things. This is a group called Coder Dojo. It's everywhere in the U.S. It might be international. We have our own little branch in Boulder, and it's hosted through the public library. Every Saturday they have some STEAM event, science, technology, arts. They do all kinds of things. We host one a month, and we do all different events. So we do a lot of Scratch. Also do a lot of Arduino. The problem with having them interact heavily is that they are really loud.
Yeah.
And they move a lot. And also, little boys take over, especially something like Scratch, where it's a game. They're building games. Little boys get a little bit annoying, really. Like they start dominating. So we have to be very careful about them not running over, both physically and verbally, the smaller kids. But we've done things like purely physical computing. We did code breaking. They were given ciphers and they had to go solve ciphers, and they did that as groups. It was a zoo, but they figured it out and they did interact. And we tried to keep them to at least some kind of restricted age range when they're interacting because of those issues. We always have parents; they have to stay.
Yeah, I was going to say the parents are important.
Yeah, they're important. Partially so they can just read over their shoulder. But so some of the kids, they start with Scratch and they start making the cat move and meow, and they're writing Python. Now in the summer we're hosting open hack sessions where we just go and hang out and they come and code, and this little kid's writing full-on Python code and they're under 10.
That's great.
So it's a good program, and it's amazing the things they'll do.
Yeah.
If you just don't tell them they can't do it.
Right.
Which is tough. Actually, handling the parents and handling the way the parents interact with the kids is the most difficult part.
Yeah, I think it's important for building that confidence, that empowering that you were talking about.
Yeah.
Building the confidence at that age. Maybe they're not interacting as much as they would, as older kids would, or we do as adults. But I think it instills that in them when they're younger, so that they're more able to do that when they get older. So I commend you. I think it's fantastic.
Yeah, I think we should be doing more of it.
Yeah.
Something I've been trying to do, and I didn't want to get into this topic, is try to get more women involved. There's a lot of men involved. And part of the problem is that they, after a certain age group where they just all kind of look like adults, doesn't matter how young they are, the women are mostly kids' parents, and that's, someone's mom is helping you. That's just not cool. So I'm trying to get more women to get the little girls excited, and they're doing good things. They're doing really crazy things. So part of the problem is that a lot of the programs that exist, like Scratch, are game-based, and that attracts mostly boys. But if you get them young enough, they will do cool things.
Time for one more question? David?
So I saw your list of best practices there, and I think that's very great for making what I would call community software. And I was wondering if you had a comment, because so much of the people are self-taught. I had this experience where the students just think, oh, we get to code to rent. And so then they hand in assignments, and it doesn't have any of these best practices in there. And I say, this is an acceptable code. It runs, but it's not what I would consider community code that you could use beyond just that person. Can you comment on that? Have you seen that?
No, I don't know if I can say much. I've never taken a formal programming class. Every programming class I have seen doesn't really focus on having community code, and they have deadlines. And sometimes your code just doesn't work. And it means that you have a time limit, and it means that you can never get it to work, and you don't learn if you never get it to work because you didn't fix it. So you do end up turning in whatever works. Something that I've realized is since I've started talking about this, just the awareness of the fact that I should be writing tests means that I write tests. I don't know if you can do that in a class. I would love to know how, if you figure it out. But yeah, I think formally teaching computer science is really hard, especially for non-computer scientists.
Yeah, let's thank Mariela again.